Welcome back. So we'll begin with few observations. So this is the first observation. You see that whenever you add two numbers and you change the order of the numbers, so here you see the answer remains same. 2 plus 3 is equal to 3 plus 2 and this 2. Okay. So from this examples and our experience from school days, we can see that for any real number, a belongs to R and B belongs to R, we have a plus b equal to b plus a. So this property will take this thing as a fact of real number. So this is our first property, and this will be our second property. The same type of property with respect to addition we have in the multiplication also. In multiplication also, when you multiply two number and you reverse it, the answer remains the same. So here also, if for a belongs to R, b belongs to b, we have a into b is equal to b into a. So we call it commutative property under multiplication. Then you have 2 plus 3 plus 6, and here we do the 3 plus 6 first, then we add to the result 2, so we get 11. So here 2 plus 3 is 5, 5 plus 6 is 11. So you see both the sides are same, and whenever you find out the left hand side and right hand side of this part, which you have already done in your school days, so this is a valid observation. So we can see that we can generalize this thing to any A, B, C belongs to R, and we call it the associative property under addition. Similar to the associative property of addition, we have this thing, the associative property of multiplication under multiplication. Then with respect to addition, we have a special number. Whenever you add this number 0 to any number, the number doesn't change. You see, 2 plus 0 is 0 plus 2 equal to 2, and similarly for root 23 plus 0 plus 0 plus root 23 is root 23. So for any a belongs to R, there is 0 belongs to R, such that a plus 0 is equal to 0 plus a equal to a. We call this existence of 0 element. Similar to this 0 with respect to multiplication, you have 1. When you multiply 2 by 2 with 1 or 1 with 2, we get 2 only. So whenever you multiply any number by 1, we get the number itself. So this is a very nice property of real number. So we take this as a axiom or property of real number, and we call this existence of unity. Then again, with respect to addition, we have this thing. For whenever you have a 2, you have a negative of that number, minus 2. Whenever you add these two numbers, 2 and minus 2, you get 0, the special element under addition. So 0 is a very special element under addition because this is the 0 element. So you see, you have 4 by 5, you have minus 4 by 5. For any number, for example, root 23, you have minus root 23 in a real number, which sums to give 0. So from this examples and our experience, we can say that for any real number a, there exists a minus a belongs to R which satisfies this condition. A plus minus a is equal to minus a plus a equal to 0. So this is called existence of negative element. So the counterpart of this in under multiplication is this. You see, for 2 we have 1 by 2, such that when you multiply 2 and 1 by 2, you get the special element under multiplication 1. So 1 is the unit element. So for any real number, you have this property. You see, 4 by 5, 5 by 4, you get 1. So if actually I was wrong, it's not for any real number, it is for non-zero real number. For any non-zero real number a, you have 1 by a, such that a into 1 by a is equal to 1, or 1 by a into a equal to 1. We call it existence of reciprocal or inverse. So in this case, you have to keep in mind that we cannot find out the inverse of 0 because 1 by 0 is not defined. Okay. Then the last property which we will take as guaranteed property for real number is this one. 2 into you see the example 2 into 3 plus 6. What is that? 3 plus 6 is 9. 9 into 2 is 18. So here you see 2 into 3 is 6. 2 into 6 is 12. It's 18. So left hand side is equal to right hand side. Similarly, you can just say this thing. They will be equal. So thus, from this, we can observe that for any real number ABC, any three real numbers ABC, you have A into B plus C is A into B plus A into C. And similarly, you have B plus A plus B into C is A into B plus B into C. So this is called, we call this distributive property under addition. Oh, sorry, the distributive property of addition. Distributive property is called, we call it distributive property over addition, like that. Okay. Next. Here is the summary of all the things what we have done here. So formalizing this above properties, we can say that on the set of real number you have two binary operations, addition and dot multiplication. The cross what we have earlier used will be dot from now on. So we call it addition and multiplication respectively, and it satisfies this property. So under addition you had we had four properties: the commutativity, the associative, the existence of zero element, and existence of negative element for each real number. So we call them, we numbered them as A1, A2, A3, A4 as this is a property related to addition. Similarly, with respect to multiplication, we have seen that multiplication is commutative, it is associative, there is just a unit element that 1, and for each non-zero real number you have 1 by A, the reciprocal of it, so existence of reciprocal or existence of inverse. So this M1, M2, M3, M4 are the algebraic properties of real number under multiplication, and you have the D. The number D is a distributive property. The two distributive property are listed as D. So these are the algebraic properties which will be used, we can use to prove rest of the results. So this will be our first result, first theorem. So we will prove this thing by using the listed 9 algebraic properties. That's it, nothing else. So you see the first statement of the theorem says that if A and B, Z and A are elements of R, means they are real number, and it follows and with Z plus A equal to A, then Z must be 0. Z is equal to 0. So that is the first thing. So we have to use this few of these 9 properties and establish this fact. So given Z plus A equal to A, so you should remember that and you see. So we'll start with Z. So Z equal to. So we have to prove that Z equal to 0 by using one of these property. We have to express Z as something else. So you can see that you can use A3, existence of 0 in R, that 0 plus A equal to A. So we can write Z as what? 0 plus Z plus 0. So this is the existence of 0 element. Now here is Z. So we cannot. We want to use Z plus A equal to A. So we want to put A there. So how can you put that? So if you see A4, the property number A4, you see that for any real number there is minus A, such that A plus minus A equal to 0. So any real number we can put in place of 0 A plus minus A. This is what I am going to do. So we have put A in place of 0 A plus minus A. Now you see now you have Z plus A minus A in the expression, and we can use the Z plus A equal to A if we can change the bracket. Yes, we can change the bracket due to the algebraic property number A2. So due to A, this associativity, we can change the bracket. Now Z plus A is given to be A, so we put it A, then it is A plus minus A, but A plus minus A is 0 by the existence of existence of negative elements. So that will be 0. So we have proved that Z equal to 0. Similarly, for the next, you see for next you have to prove that if U and B not equal to 0 are elements in R and U into B is B, then U must be 1. So This is what we have to prove. This is similar to the last result. So you start with u equal to using the property number M3, I think. Yeah, M3, existence of unit element. I can write u equal to u into 1, and 1 can be replaced by b into 1 by b, because b is not equal to 0, so I can talk about 1 by b. So by the M4, existence of inverse element, we have u dot b dot 1 by b. Now, by associativity of multiplication, I can change the order of the bracket, and we have ub in one bracket and 1 by b in another bracket. So this is by the associativity of multiplication. Associativity of multiplication. Next, now ub is given to be b, so you just put that here. It is sorry for that. It's z plus a, so b ub equal to b. Now b into 1 by b is equal to 1 by existence of unit element again. So we have proved that a equal to u equal to 1. Now next you have to prove this a into 0 is equal to 0. It is not given in the algebraic property, so we have to establish this using the 9 properties given to us. So we started with a. So this is in trial and error thing. So first we will put a equal to a into 1, because by the existence of identity element. Now next we can put 1 equal to 1 plus 0. This is the existence of 0 element. Now you can use this distributive property to get a into 1 plus a into 0. This is the distributive property of multiplication and of addition. Next, a dot 1 is equal to a by existence of identity element. Now you have a equal to a plus a dot 0. If you remember, in the part 1 we have proved that z plus a equal to 0 implies z equal to 0. So you see we have a similar expression here, a equal to a plus a dot 0. This means what? In place of in part 1, if you see that the z is what? A dot 0, and a is a only. So z equal to 0 means we should get a dot 0 equal to 0 by part A. So this is how we do the things. Okay. So whatever result you prove here, you can use that thing in the later later results. Okay. But only thing is that you have to mention from where you are getting you are taking this. Okay. So there's the thing. So you see these are two. I have just written these two results here only to show that this A and B are similar. Okay. A is a result with respect to addition. You see in place of z, if you here you see if you change the z this plus to dot, you will get this one. And because 0 is the special element of addition, and under multiplication 1 is the special element, so 1 is here. So 1 is the 0 is the 0 element, 1 is the unit element under multiplication. Okay, these two results are very much same, so their proofs were also very much same. So now next we have two more result. We'll do two more result very quickly by using algebraic property of real numbers. So this is the first one. So let's go through that. So these are the properties we are going to use. So first result is this one. It is I've just copied this thing from the book. So you see, first we start with, here it is given a b equal to 1, so we have to prove that b equal to 1 by a. So b equal to 1 by a, this is what we have to prove. So we start with b. I can write b equal to 1 into b by existence of unit element. Now again, as a is not equal to 0, so I can write in place of 1, I can write 1 by a into a by existence of inverse. There is m4. Then now you can do by associativity. I can change the order of bracket, so this bracket will be here. So you see this is m2. So now it is given that a dot b equal to 1, so it is 1, but this into 1 is 1 by a. So we got b equal to 1 by a. Similarly, if a dot b equal to 0, either one of them must be 0. Okay, whenever you multiply two real number and you're getting 0, so one of the real number must be 0. That is the result. Okay, we know this is a fact, but what we So we are here to prove this thing by using algebraic property of real number. That is all. Okay, it's very simple. So here we have. So we first of all we'll assume that a is not equal to 0, because if a is equal to 0, then we are done. Okay, a dot b equal to 0 and a is equal to 0, so there's no problem. We have the result. So we start with a is not equal to 0, and we want to prove that b is equal to 0. Okay, so you just start with this. We multiply 1 by a in and add a dot b. So you change the bracket by using m2. Now by existence of inverse element, this is 1. So you have a b here, so you got a b. Okay, but since b a dot b equal to 0, we know that this is given here. Again, if you see this part, so 1 by a dot b dot 0, or b dot 1 by a dot b. So but this thing is 0, so we can get a 0 here. But we are but earlier in result we have proved that a into 0 is always 0. Okay, in the c part of the first result. So from the c part, this is the reference from the book. So from the c part we get this is equal to 0. Sorry, 1 by a into dot equal 0 equal to 0. So you just combine these two. This left hand side is equal to b, and this left hand sides are same, so they must be same. So b equal to 0. That is the thing. Okay. Further, if further one more result I want to do, a few more results we want to do. So you see a plus b equal to 0 is given, so we have to prove that b equal to minus a. So that is the aim. So we have to use these properties only. Okay, this 9 properties, and the results we have what we have proved. Okay, so we start with b. So I can write b equal to b plus 0 by existence of 0 element, and we can replace the 0 by this a plus minus a by existence of negative element. Now you do by associativity, change the bracket. Now it is given that a plus b equal to 0, but we are getting here b plus a, but we know that a plus b equal to b plus a by commutativity, so change the order of it. Now you just substitute as it's 0, and 0 plus minus a equal to minus a by existence of 0 element. So basically what we have proved is b equal to minus a. Okay, now minus of minus a equal to 0. So this result is very much uh, it's little bit it's look complicated a bit, but I'm sure that you will understand this. So for any real number r by a4 existence of negative element, we said there exists minus a, such that this result is true. A plus minus a equal to 0, and minus a plus a equal to 0. Okay, similarly by a4 again, for minus a, there exists minus of minus a in R, such that minus a plus minus of minus a is equal to 0, or minus a minus minus of a plus minus a is equal to 0. So we have, first of all, here we have taken a as the first number and minus a as the negative of it. Here our number is our real number is minus a, so this is the negative of minus a. So we want to prove that negative of minus a is a itself. Okay, this is what we want to prove, and this effect, you know, that minus into minus is a, so that's not a big problem. Okay, so that is the thing. Now let's go to the next step. So we start with this expression. Okay, a plus minus a plus minus minus of a, this is equal to a plus minus of a plus minus minus of a. This is due to associativity. Okay, I have just written the associative expression for three numbers a, minus a, and minus of minus a. Okay, that is the thing. Now a plus minus a is equal to 0 from the first expression. Minus a plus minus of minus a is equal to 0 from the second expression. So that is the thing. This is 0, and this is minus of minus a, it will remain like this. This is a, and this part is 0. Now 0 plus any real number is the real number itself by a 3, I think, existence of 0 element. So this existence of 0 elements, so I have to write the reference here. I hadn't written that, so this will be this. So this will be minus a minus a, and similarly here also a plus 0 will be a. So this a. So we got minus of minus a equal to a. Okay. So next, just say we define subtraction as addition. I mean, subtraction is a minus b. So a minus is b is theoretically it's basically it is sum of a and minus a. Similarly, a divided by b is what? A into inverse of a. Okay, and you have few definitions here. For example, a to the power n plus 1 is a to the power n into a, and this you see a to the power n plus 1 is a to the power n plus a, and you know what is a square? A square is a into a cube is a into a into a. Similarly, a to the power 1 is a, and a to the power 0 for a not equal to 0 is 1, and a inverse is equal to 1 by a, and for its natural number n, a to the power minus n is equal to 1 by a to the power n. Okay, so this is the thing. So we can do the use this freely in our exam exercises and all. Okay. So there are a few notations which I want you to recall. This for natural number we use this n. For real number this r. You know this, okay? And here is a definition of rational number. So a rational number is a number of the form b by a, where a, b are integers and a is not equal to 0. So and there are a set of rational numbers. So we know that real numbers are rational numbers are subsets of real number, but to prove that there are numbers which are not rational in real numbers is not that obvious. So we'll start with one of them. So we'll just show that square root of 2 is not a rational number. So basically it will be irrational number. So irrational number is a number which is not a rational number. So here is the thing. So before proving that, I would like you to recall two more things. Even number and odd number. So even number is a number which is a multiple of 2. So that is we can write that thing as 2n for even natural number. Okay, so it's 2n, and even odd natural number can be written as 2n minus 1, where n is a natural number. So you put n equal to 1, you get 1, n equal to 2, you get 3, n equal to 3, you got 5, like that. Okay, these are the two expressions for even natural number and odd natural numbers. Okay. And every natural number is odd or even. You know that there is no natural number which is both even and odd. So these are two facts. So we want to prove that there is no rational number whose square is equal to 2. So we start with this. Suppose that there is a rational number whose square is 2. Okay. So let's take it. So if it is there, we will find p and q, value of p and q as they are integers. Okay. So we'll take this thing, we'll assume that the border is positive number, because it doesn't matter because we are taking the square, so square will be always positive. That's not a big thing. Okay, now next, n, we will assume that they don't have any common factor other than 1. So they are co-prime numbers, so they don't have common factors. Okay. So now you just square this in both sides, squaring in both sides, so you get p square equal to 2p square. Okay, so that's not a very big problem. Or you just say that you can multiply it by p square, inverse of p square, whatever you say, you get it. P square is equal to 2 into p square. Now you see p square is equal to 2 into p square, means p square is in the form 2 into p square, means p square is an even number. Okay, so p square is an even number. So if p square is an even number, I would like to say that p is an even number. Okay, this is what I want to say. This implies p is also even number. Why is p is even number? Because if p is not an even number, then its square cannot be a even number. You see, if p is an odd number of the form 2n minus 1, okay, because if it is an odd number, it will be of this form. Now you square this both sides, so p square will be 2n minus 1 square. So this will be 2 into 2n square minus 2n plus 1 minus 1. Okay, it's an odd number. Okay, next, is odd number. Okay, therefore P must be odd number. Okay. So since P and Q doesn't have common factor, doesn't have 2 as a common factor, so Q must be an odd natural number. Okay, because we have assumed that P and Q doesn't have a common factor, and we have got that uh, P is an even number, so Q must be odd number. Okay, so now since P is an even number, so P will have a form 2m, m is a natural number. So we put this thing in the earlier expression, and we expression where P square is equal to 2 into P square. So we put that, you will get 4 m square is equal to 2 Q square. Okay. Now from this you get 2 m square is equal to P square. Okay. It says that Q square is an even number. Therefore Q square is an even number. Again from the same argument we will get Q is a even natural number. Okay. Since our hypothesis was P by Q, it should be P by Q square equal to 2 leads to contradictory conclusion that Q is both even and odd. So earlier here we got Q is odd, and here we got Q is even. So we are getting Q is both even and odd, which is not possible because every natural number is what? Odd or even. Q is a natural number. It must be odd or even. It cannot be both. So this is a false. Okay. As this is false, so we started with one assumption that P by Q square is equal to 2. That is only an assumption what we have made. The rest of the thing we have deduced from that. So we can say that our assumption was false. So means there is no rational number whose square is equal to 2. Okay. So now using the algebraic property, I would like you to solve this thing. Okay. Prove this thing. Okay. A plus B equal to 0, then B equal to minus A. I think I have done that. B part also I have done that. Okay, there are there are only few what I have done, and rest of the thing you have to do. Okay, that is what I want. That will be the end of this first lecture, I will say. So thank you. Hope you understand this. You will do the things and try to develop yourself. And if you have any problem, you can ask me directly. Thank you.